Thank you for the opportunity to speak. This is great. I'm not sure I've ever been at a conference where almost every other talk is an introduction. So I can conceivably just sort of start like halfway through, but I'm going to be nice and we'll actually like yeah. So you'll see a lot of the ideas that have been presented so far in other people's talk. All right. So first, everything is joined with Sam Lisi and Chris Wendl. I'm doing this Spinal book thing. Okay, so all right, we're looking at essentially this picture over and over and over again. Right? So I want to understand all sort of symplectic things that bound a given contact state. And everything looks like this. So you know, call this guy alpha, but it doesn't really matter. So the idea is that we've got a four manifold, or in general we're going to be talking about an n-dimensional manifold that, let's say we've got a four manifold. We want this to be symplectic, so we want some two form on X, which is not degenerate. So we want omega, which is omega, to be positive. Okay. We also want a contact manifold at the boundary. It's much bigger. We want this guy to have a one form, and we want alpha with G alpha to be positive. And we want these guys to match nicely. And for that, I want a vector field that's sort of pointing out everywhere. L, so that if I contract L into omega, I get alpha. Okay, so this is the setup, and this is the kind of picture I want to understand here. In this case, everyone knows a lot of this example, but for B4, we can take just omega to be dx1 wedge dy1 plus dx2 wedge dy2. And if we take the actual Albert radial vector field, then we can take, on S3, we can take alpha to just be x1 dy1 minus y1 dx1 plus x2 dy2 minus y2 dx2. And if we restrict to the unit sphere here, we'll get an actual contact form on S3. And if you want to, you can sort of pick one direction, and you'll get the actual contact form that we're used to seeing on R3 up to some sort of scale here. So for example, if you decided to take y2 is equal to 1, then you've got y2 is equal to 1, dy2 is 0. I suppose I chose the wrong orientation on a lot of these things, but then sort of near that one point where y2 is equal to 1, you've got a contact structure that looks a lot like the contact structure you're used to seeing on R3. Okay. All right. So, data compression. Manoj talked about this object called a Lefschetz vibration. And what a Lefschetz vibration is essentially a topological way of encoding, say, a symplectic structure, modulo some weird equivalencies, and it's incredibly useful for constructing examples because it is data compression. So it gives you a very easy topological way of describing what your symplectic manifold is. So Lefschetz vibration is going to be a map. Let's start to D2, which is almost everywhere going to be a fiber bundle, except that sort of isolated critical points, you've got Lefschetz singularities. So topologically, what you have is over a regular point, you've got, say, a surface with boundary. And over a singular point, you've got a surface with a cusp. So,
you mean a node?
Sorry.
You mean a node, right?
A node. Sorry, yes, with a node. Yes, not a cusp. Good. Thank you. Yes. Sorry, it's nodal surface. Yes. So what you've done is, as I sort of move from, say, the smooth fiber over to the singular fiber here, you see that there's exactly one of these curves making sort of pinched off. All right, and there's a handedness to this pinching, which means that if I sort of look at a small loop around one of these singular fibers and I sort of see how does my fiber surface change, there's an actual sort of non-trivial gluing map. There's a monodromy that happens around the singular fiber. And that monodromy is a Dane twist about this curve here. So this is my what's called the vanishing cycle. This is the curve that gets pinched off around the singular fiber. And as I go around this, my surface is changed by a Dane twist about this curve. Okay. All right, so not all symplectic manifolds have such a structure, but certainly sufficiently nice ones do. There's Stein structures. These are the symplectic manifolds that come from homomorphic submanifolds or analytic submanifolds you see in. And just out of ease, this is sort of what we're going to focus on right now. This is the type of object you can get in this. Okay, so what is the actual sort of data compression then? This symplectic manifold is actually described then by this surface plus this sort of ordered collection of vanishing cycles here. So if I pick some sort of reference point right here, and I pick some arcs out to these singular points, then I've got an ordered collection of vanishing cycles here. So this gives me a shorthand or a specific way of describing my symplectic manifold that I explore with this structure. Okay, so this is I don't know old, but it's certainly standard. It's informed by algebraic geometry, and it's used in the closed case as Anash was talking about. But we're going to talk about it in this case with boundary. And the nice thing is that we'll also get something on the boundary of this formanifold on Y that's sort of similarly a form of data compression for our symplectic manifold, or our contact manifold. So on the boundary, so what's the boundary of this object going to look like? Well, if you look at the boundary of this, you get sort of a Kumith formula for the boundary manifold. You've got sort of two pieces to this. So you've got over the boundary of the disk, well, what do you have? Well, each of these is going to be a smooth fiber. So you've actually got sort of a fiber bundle over the disk. Over the circle. So over the boundary of the disk, you just get a fiber bundle. And the monodromy is determined by these vanishing cycles right here, right? So if I go around this vanishing cycle, I get, go around this singular fiber, I get a Dane twist about this vanishing cycle. If I go around this one, I'll get another Dane twist, and so on. And so the monodromy, in terms of this bundle, is given by just the product of Dane twists about these vanishing cycles. You also get, though, a sort of secondary boundary, right? If I think about the sort of the boundary of a product of two things, you get two boundary components. You get something over the boundary of the base, and something over the boundary of the fiber. Now, the way that we've described this, nothing is happening over the boundary of this fiber here, so you just end up with a product. So over sort of the boundary of F, you end up with just boundary of F cross D2, which is just a disjoint union of solid tori. Okay, this description is exactly what Jesse was talking about when he was talking about an open loop decomposition, but with sort of a specific sort of thick neighborhood of the binding here. So the idea is, though, when we glue these together, we're gluing this S1 to the boundary of D2, and we're gluing this S1 to the boundary of F. So in our 3 manifold, we've got sort of 2 pieces here. We've got sort of S1 cross D2, where this D2 direction is sort of is this meridional disk. But this gets glued to the fiber bundle part on the complement, where the S1 direction is now the boundary of my fiber. So if I sort of stick my surface F sitting out here, then I've got, I glue this side to this side here, and I thicken this and swing this around to give me an actual sort of bundle here. So I've got sort of fibered manifold on the outside here. I filled up everything with copies of F. And I'm gluing this to S1 cross D2 so that these two different fibrations are perpendicular. These are sort of glued orthogonally. So you've got sort of a bunch of disks sitting in here, and you've got a bunch of fibers sitting out here. Outside we have a non-trivial return map. We've got the monodromy that's expressed by this, and inside we just have a product with the disk. Okay. Okay. So this is great. Here we get a symplectic structure coming from the Lefschetz vibration. Here we get a contact structure, which comes from Thurston-Winkelnkemper's construction. So you can think about it as being essentially a deformation of the tangent spaces to the surfaces here, but also as a deformation of the tangent spaces to the disks. So what you want to think about is the contact structure is going to be something that's sort of pretty close to being flat everywhere. But as you come into the binding, you're rotating in this left-handed manner up to being vertical, so that you're sort of tangent to the disks here. So I've sort of oriented everything in my head, but not to you guys. So here we go. Let's orient F. This gives an orientation on the boundary. This is going to give you the sort of the positive normals orientations on the disks. And on my contact planes are sort of like flat everywhere in the fibered part, and then they rotate up and they're sort of flat everywhere on the sort of disk part, but there's this sort of intermediate torus region where everything's sort of rotating. Is this clear? So we want this whole picture to be sort of essentially locally S1 invariant. So here we've got sort of flat tangent spaces. Here we've got flat tangent spaces, and in between we're sort of rotating in a left-handed way that is impossible to draw. Okay. Okay, so I do want to mention that that this picture sort of extends to the entire contact world. So there are many contact structures that don't arise as the boundary of, say, a Stein manifold. And there are many open book decompositions that are compatible with them that don't necessarily show up as the boundary of a Lefschetz vibration. So this picture of an open book decompositions explaining contact structures is the work of Giroux. And it's one of the sort of, again, it's data compression. So it gives us a very easy way of describing a contact manifold just in terms of a surface plus a monodromy. But we're going to focus on the specific situation here, which is when does this object arise as the boundary of a Lefschetz vibration? And, okay, so the one caveat with all of this, as Jesse mentioned, is that there are infinitely many different open book decompositions for a given contact manifold. And it's impossible to tell whether or not the one you're looking at actually comes from the boundary of the symplectic filling, if you even know that it exists. So supposing that you're shown some symplectic filling, without knowing the Lefschetz vibration for that, you don't know whether or not this open book comes from that particular, is it any related to the Lefschetz vibration for that symplectic filling? Okay. Okay, so this is sort of, I think, what makes this an interesting, sort of, still interesting. If this had solved everything, that would have made for a great but very sort of short subject. Okay, so, excellent. All right, so I want to sort of answer this question, at least in a sort of easy case, using some old work of Chris's. So, so this issue about whether or not you've got the right open book to talk about your symplectic filling was answered by Chris. And what it says is that if F is genus 0, then any symplectic filling of your open book Fb admits a Lefschetz vibration whose boundary is Fb. So in particular, if you have a planar open book, something where the page is genus 0, then every symplectic filling comes from one of these factorizations of your monodromy into right-handed dating twists.
So, sorry, if F is genus 0, any symplectic filling FV refers to
sorry.
free manifold.
Oh. Sorry. Any symplectic filling of FV in this level version boundary is. So in particular, yes, the filling is going to come from a decomposition of the monodromy.
This doesn't require Stein.
It doesn't require Stein, but it is. But the corollary is that it is Stein. Yeah. Yeah. And if I sort of add Niederkruger in here, you can't see it there. Then I can make this symplectic filling weak. So it says that in this particular case, not only is a sort of this type of nice compatible filling that I talked about before going to be Stein. Any sort of weak generalization of a symplectic filling is also going to be Stein. So this is I love this theorem. It's why I'm doing all of this right now. Okay, so what can you do with this? Well, Olga Plamenovskaya and I use this to talk about some symplectic fillings of lens spaces. Let's just look at one particular example, though, which isn't too related to that, but or isn't our result, but is related to this. So, if we look at the lens space L41, this has a contact structure that descends from S3. You can describe this as this has an open book decomposition whose page is a four-punctured sphere, and whose monodromy is a right-handed Dane twist about each of the boundary components. So when I describe my contact structure like this, I actually am handing you a symplectic filling where I construct a Lefschetz fibration whose fiber is a four-punctured disk, and whose Lefschetz singularities, there's one for each of the boundary components. Okay, this monodromy though has a second factorization. You can write this as the lantern relation as a product of three Dane twists. Here, and I'm going to go sideways and run around back. And if I describe it in this way, where I've got these three Dane twists now, this is the boundary of the disk bundle over S2 with Euler number -4. And this object is the symplectic filling that you would get by removing a degree 2 curve from CP2. So this is the complement of the quadrate in CP2. Okay, then the one thing that you should possibly take away from this is that as a disk bundle, this thing has the homology of a sphere. This is a rational homology law. So there's no homology, no rational homology in this object. Okay, but here's an example where two different factorizations are going to give you two different fillings. And it turns out that these are the only two symplectic fillings of this contact manifold. It's easy to show just from the description of the monodromy here. I guess maybe it's not easy, but if you apply some theorems today of data model, you can get to this answer. And then, okay. All right. So what I want to do is sort of push this in the other direction slightly, which is there's lots of things that you sort of expect similar results from. Lots of contact manifolds you expect similar results from, but they don't have, or for whatever reason, they don't admit a planar open book decomposition. So what I want to do is I want to expand this idea of planar, and in order to do that, I'm going to expand what our idea of a open book decomposition is. So before, an open book, we can think about it as it's a decomposition of Y into a fiber bundle, and some number of product manifolds glued along this sort of boundary tori in this perpendicular way. So let's generalize this to, say, what we're calling a spinal open book. So we're again going to take our three manifold and decompose it into, let's sort of put a hat here for reasons we'll show later. But instead of, we've got a fiber region here, but instead of taking our product region to be just S1 cross D2, we're going to generalize this to be S1 cross some other surface. So this is going to be S1 cross, say, some base manifold B. Okay, that's all spinal properties. So it's exactly what we had before. We're looking at now just a picture where I'm going to draw genus on both sides here, say.
So this is why you had such a quick answer to Inach's question?
Yes. Yes. So here's F, here's B, and I'm looking at sort of gluing the front and the back pictures together again. And now there's sort of, sorry, that's supposed to be genus. Now there's not necessarily like a link that's involved. What you have is now just some other product manifold that's sort of acting as your binding, and that's what we're calling the spine. Yes.
So is B always punctured once, or could you have more than one puncture and fill more than one component?
You can have, yeah, B can be any surface. You can have multiple boundary components, and yeah, exactly.
For both F and B?
For both F and B, yeah. So here we describe this usually as, just as data compression, we describe this as a surface F plus some Dane twists. Some ordered collection of Dane twists giving you the monodromy. Here we need a little bit more. Here we need sort of F hat, B hat, a gluing path, which tells you how to identify the boundaries of F hat and B hat. And then you also need some Dane twists on F, or F hat.
These three manifolds that are necessarily toroidal, and just right.
If the base is not a disk, then they'll be toroidal. That is not a disk, and even in that, I wasn't entirely sure that you could guarantee that. I'm not sure that, because you could sort of you could chain together like.
Well, this is on D. There is a trivial product, right?
Yeah.
So if you take some genus, you'll get it.
If you have an essential curve in the vertical direction, you'll get a torus. Yeah.
What is hot?
So hat just means here that usually we think about F as being connected. Here, F can be disconnected. Both F and B can be disconnected. So that's another important point. Yes, not only can they both have multiple boundary components, they can be disconnected. So I try to draw things, or I tend to draw things similar to this picture here. So for example, if you take both F hat and B hats to be, say, a punctured torus, and you have the monodromy being trivial, then you would have decomposition of your manifold into something that sort of looks like this. So you've got S1 times a punctured torus, and let me sort of just open this up a little bit. So here we've got S1 times a punctured torus. You're still going to have S1 times a punctured torus, but it's sort of perpendicular here. So I'm just going to glue the front to the back again. Then in this case, what you have is that the Y3 is going to be a plumbing of two copies of T3, or two sort of S1 cross a torus, right? I mean, that's exactly what we've done here. We've taken T3 and we've removed a fiber, taken T3 and removed a fiber, and then we've glued them together. Instead of matching surface to surface, we're sort of matching perpendicular here.
So is it the boundary of plumbing of two disk bundles over T2?
It's exactly that, yeah, that's right. So you could if you were going to sort of give a Kirby diagram of this, you would just sort of give the sort of I don't know if I can do this on the fly. This guy's not really great.
Just the boundary of the neighborhood of the union of the axes in the 4 torus.
Right.
Ah, yeah, that's exactly it.
Yeah.
Yeah, so that's exactly the point here. the reason we started looking at this is the kind of decomposition you would get if you looked at a Lefschetz vibration whose base is no longer going to be a disk. So again, there's a relationship to symplectic fillings and to Stein manifolds. So if I take a Lefschetz vibration, but now over something of genus, something of positive genus, then I'm again going to get a decomposition into some sort of Lefschetz singularities over the boundary of the torus here. This is a confusing torus. Let me do this. We're just sticking out over here for some reason. So over the sort of singular points, you've again got sort of Lefschetz critical points, Lefschetz singularities. And now over the boundary of this, we get our fiber part. Over the boundary of the fiber, we get our spine region. We get the boundary of that across the base here. So this is going to be F. This is going to be B. Okay. So sorry.
Do we have a sensible way to stabilize these?
No. Yeah. So that's one drawback. Unlike in the over the disk picture, where there's a sort of way of increasing the genus and the complexity of both the open book decomposition and the Lefschetz vibration, there's no way of doing it in this computer. So it's somehow much more rigid because of that. Yeah.
But if you assume from the beginning that you didn't have multiple components, and that's it.
I think even there it's hard. But the issue is that the reason it works for the disk is that the one handle you're attaching is a one handle across a disk. Like it's a two-dimensional one handle across a disk. Here, if you attach something to the fiber, you're attaching a one handle across the surface, and that changes the topology. Yeah. Okay. Okay. Well, there's two things that you get out of this. The first is that there's a topological obstruction. Sorry, so this guy continues to double overdrate. Not that anyone can see what that actually is, but if you know what the Kirby diagram is, then you know what the Kirby diagram is. So, you know what I mean. Right. Sorry. There's now two different obstructions to admitting symplectic filling here. Before, all we had was the monodromy. Now there's actually some sort of connectivity issue between what's happening here and what I'm sort of describing as a spinal open book over here. The point is, if I look at the boundary of a Lefschetz vibration over a non-disk base, every component of the fiber here is glued to every component of the base. So if I think about what's happening on the boundary, if there really are two components of F here, when I glue these up to get a spinal open book, sorry, two components of the boundary of F, I'm going to get two components of S1 across this base. If the base happens to have more than one component, I'm going to get sort of two distinct fiber buckle regions, but each one of those has to be glued to a copy of the base. So if your spinal open book comes from a Lefschetz vibration, then every component of F is isomorphic, every component of B is isomorphic, and every component of F gets glued to every component of B. So it's sort of like universal connectivity that picture what's happening here. Okay? The idea is that sort of as I round, if I look at one of my fibers here, around the corners, every boundary component of F is going to hit all of the different boundary components, or all of the copies of B. Okay, so let's look at some examples of how you can use this. First things first, though. Let's generalize Chris's theorem. So the first thing that the reason we did this is that this allows us to generalize what planar is. So if the spinal open book, you can spell sometimes. And let me give you the information here. So we want F hat, B hat, a gluing map, and a monodromy has a planar component to F hat one of the components of F is planar, then Chris's theorem holds. That is, then any symplectic filling of this has a Lefschetz fibration, whose boundary is your spinal open book. I did not. Yes, that's a good question. Sorry. Yes. So, yeah, let's do that. This is good. Sorry.
So this gives you lots of ways of getting lots of non-symplectically fillable things?
Yeah, yeah. So I'll do a family of examples here in just a second. But in order to see the context structures, yeah, we should talk about what this is. It's exactly the same picture as for the normal open book. We expect the contact planes to be sort of roughly close to being tangent to the pages here, as well as being roughly close to the tangents to the spine region, to the fibers of the spine here. And then in between, we just have a rotated region, where we're sort of rotating from being flat to vertical. So it's exactly the same picture. Yeah, so let's look at a family of examples for this theorem. The easiest family to construct like this that has a planar region is if you look at a situation where F is an annulus, or many copies of an annulus. So I don't need it on the boundary. Okay, so examples. So if F hat is a union of annuli, I don't need to say any of this. Well, what sort of object would you get here? Well, let's draw this sort of this spinal open book picture where I've got both F and B and the gluing map shown. So here I'm going to get a copy of F, and the squiggly line means that I'm gluing one boundary component of F to a boundary component of B. So in the closed manifold, these two curves aren't going to be parallel, they're going to be perpendicular. So here's where I sort of cross from being in F to being in B. And let's put another sort of annular copy of F here, and let's put sort of like two annular copies of F here. And again, we're going to sort of want some monodromy, so let's put some day twists in here. Let's call these guys positive type.
So the B there is disconnected.
B is going to be disconnected. So here's another copy of B. F is disconnected.
So in the Lefschetz vibration, you're wrapping down to B, right? So that means the format is disconnected.
This is the first example of something where you can't admit a symplectic filling for exactly this reason.
Oh.
These two components to B are non-isomorphic surfaces, so this is not the boundary of the Lefschetz vibration, so this cannot be fillable. What this is, though, is a very easy to describe symplectic or contact manifold. So what this is something where the contact planes are sort of roughly tangent to the surface here, but as I go across this sort of squiggly line, as I go across what we call the interface torus, it's going to rotate up to being vertical. And because we're looking at a picture where all of the copies of F are annuli, as I sort of cross around this region here, I've got something where I'm sort of, say, tangent to B, and I rotate up to being, say, vertical at F, and then I flip back over to being tangent to B over here. So, something is wrong with this picture. What am I doing? This isn't a bundle because I've drawn things in a non-picture way. You don't know what I'm saying. Okay.
So over F, you have disconnected F, and there is components on which monodromy is trivial, and then you have one component where you put in some twisting, right?
One component where I twist in some twisting. So what this is this manifold is going to be, in some sense, an S1 invariant contact structure on a circle bundle over a non-orientable surface. So what I think about is I'm going to glue all of these things together, but I'm gluing by an orientation reversing diffeomorphism as I cross F. So this is going to give me a sort of a non-orientable surface base, but in the total space I'm getting a contact structure over sort of a circle bundle over this space. Let me give you something that's sort of slightly easier to visualize, which is if we actually assume that the base is orientable. So what do we want to do for that? Let's fill these guys. So an example of something like this, or maybe sort of most examples, is the family of universally tight contact structures on circle bundles over surfaces that were classified by Kohanda. So on S1 bundles over a surface S, we can describe a contact structure by giving a dividing set on the surface S. So a dividing set is just any collection of curves that does exactly what this does not do. It divides it into positive and negative regions, so that as you cross one of the dividing curves, you go from a positive region to a negative region. So something like, that's orange, let me make this red here. So if I did something like this, say, this would give me something that would be a dividing set because I can cross from positive to negative. So the contact structure that you associate to the circle bundle over this is sort of what I'm describing here. On the positive region, it's sort of tangent but oriented the same way. As I cross the dividing set, it flips over and becomes tangent but pointed in the opposite direction.
This is the S1 cross S that I'm talking about, right?
Yes, so sorry. I'm looking at, well, the S1 or the circle bundle version, whatever it is, on the total space of this, I'm going to get a contact structure which is roughly tangent, positively tangent to the positive regions, negatively tangent to the negative regions, and flips over as I cross the dividing.
I'm just saying, you don't see the Euler class of your circle bundle. Is it the trivial circle bundle?
It doesn't matter. The Euler class is sort of hidden in this. You don't see the Euler class in this description, and this description works for every Euler class.
So how do you see this as a final open book?
So in this final open book, we're just going to replace every copy of the dividing set with one of these annular copies of F here, right? Because what we want is the contact structure to flip over as we go across. What we should do is think about this as there being an intermediate step where we, instead of flipping all the way over, we stop, and at some point here we've got an annulus region where we're vertical. And as you sort of, at that sort of annulus region right here is exactly going to be the annular fiber of our Spinal open book here. So what we want to do is we want to think about cutting this open. Let's say we cut open right here. And if I take this arc and I sort of cross it with S1, that annulus is going to be one of the fibers of my Spinal open book.
Why is it no orientable?
Oh, because I did something dumb here where this isn't a dividing set. When I flip over, the contact planes are flipping over, but my surface is sort of staying the same. Or like, what am I trying to say here? This has to flip over sort of exactly once as I go from here. So here I'm rotating by 90 degrees. Here I'm rotating by 90 degrees again. So this gets glued to this, but with the opposite orientation. So,
I don't see, in the way you're describing it, right, your portions, the things that are not annuli are just products in this one. Right?
Yes.
And then the things that are annuli might contain some monodromy.
That's
but
right.
You're not describing any monodromy in that picture.
Not yet.
are you?
Not yet.
So right now, as it stands, this is a picture of S1 cross S.
Until we either just the monodromy and the Euler number are going to be the same. Yeah. So as I haven't drawn any monodromy because we're just
right
looking
now,
at
this is S1 cross S.
yes, sure. Okay, but if I want to turn this into a Spinal open book, then I can fix whatever monodromy I want, and that will change or fix whatever Euler class I want for the circle bundle. So all I'm doing is I'm going to replace every red curve here with one of these sort of pairs of orange squiggly lines, and that's going to give me exactly the Spinal open book. So here I've got one copy of F. Here I've got copies of F. here I've got copies of that.
Jeremy, can I try one time to say what I think is going on? So the top surface is the base. There's some circle bundle over that base, right?
Yes, that's right.
not a spinal open book, that's just a plain old surface as the base of the circle bundle.
Yes.
The red arcs are dividing set.
Yes.
Then I take, for each red arc, I take a neighborhood of it. That cuts, then I can take the complement in the base, and that's some surface, which is going to end up being B hat.
Yes.
Then I take, for each of the neighborhoods of the red arcs, I take a transverse arc, and an arc cutting across that annulus, and I take its inverse image in the 3 manifold, is the set of fibers sitting over that, and that's also an annulus. Sort of coincidentally is an annulus. The annulus going this way around the neighborhood of the red arc is sort of not really what we're talking about. It's the annulus that's the inverse image of that.
That's right.
And that collection of all those, one for each red arc, will be F hat.
Yes.
Is that correct?
That's right.
So now we described some. Oh, but we don't know. We also need to lift each component of the complement of the red arcs actually into the 3 manifold some way. The B hats should be embedded, but that's also because there's trivial there.
That's right. So we're assuming that the bundle is trivial
Trivial over
everywhere.
each piece, right?
Yeah, and we're just gonna pick one of these guys to where we use shearing to the circle bundle. And so let's suppose we sort of make sure we exactly have the projection so that we've got our shearing, we've got sort of our sort of shearing happening in this balloon. That means that when we describe this as a spinal open book, this is where we're going to run a monodromy. Okay, so this is sort of an infinite family of contact structures. They're all universally typed. If you essentially give me a circle bundle, give me a surface and an Euler number, give me a dividing set, that will construct a contact structure, or that will sort of determine a contact structure. That contact structure is determined by this spinal open book. And what we see is then, unless we have a very specific description of the contact structure in terms of the dividing set here, there's no way for this to be the boundary of a Lefschetz fibration. So unless both the positive and negative regions are isomorphic, and they have to be sort of 2 copies, right? They're both going to be glued to copies of F here, you're not going to be fillable. So that's exactly the obstruction here. So of all of these contact structures, the only ones that are fillable are the ones that are sort of doubles and have, where the contact structure has to say Euler plus 0. So this is not fillable. If I did something like this, this would give me something that's fillable.
But you could also have several components on the left and the right.
They have to be, because if we think about this being the fiber, this only has 2 boundary components. So it's got 2 places where you're going to glue on copies of the spine. So there can only be 2 copies to the spine here. So B has to be 2 different surfaces, and they have to be isomorphic. So these are the only things that are fillable. Now most of this it's much easier to show that these are not fillable using flow homology. So Coe and Will and Gordon, they showed that for most of these things, the contact invariant is 0, so they can't be fillable for that reason. But there's a few things you can sort of see from this that don't show up there. But this is nice because it's a very easy picture to sort of to see. This is sort of what happens with it. And yeah.
Do you have the needle Kruger extension to yours as well, so that this works? This doesn't work for me.
It doesn't work, in fact. So so one more example of something that's weakly fillable is we look at T3, but with the sort of with Giroux torsion. Let's say C2 here. So this is going to be the contact structure that sort of does 2 full twists as you go around in the S1 direction. This has a spinal open book that it's a circle bundle where we're looking at this picture. So each time you sort of cross here, you're flipping one. So here we've got sort of half a rotation. There's your full rotation. This gives us 2 rotations. When we turn this into a spinal open book, we now have 4 copies of F. And even though all of the copies of the base are isomorphic, there's too many of them. this bijection between components isn't satisfied, so this can't be fillable. But this does admit a planar spinal open book. So it's not true. There are weakly fillable planar spinal open books that are not strongly fillable. Yeah. Okay. Questions? Okay. All right. So so let's talk about sort of the other direction. Oh, this is the great part about this too. For those things that are fillable, there's a unique filler. You can describe it precisely by this exact Lefschetz vibration, and there's no other way to do this. So no matter, essentially because the fiber is an annulus, there's sort of no non-trivial Lefschetz vibrations you can construct. So that's the other side. For those things that are fillable, filling is unique. Okay, so let's see if we can destroy that. Just in the circle bundle case, yeah. Well, in essence, anytime your fiber is an annulus, then you're okay. There's some weirdness about, not in this situation, but maybe in this situation. Yeah. Sorry. But yeah, whenever the fiber is an annulus, if you admit a filling, the filling is good. Yeah. Okay. All right. So let's destroy that. How do we find something that has infinitely many fillings? So the idea is essentially sort of stupid. If we think about our Lefschetz vibration is sitting over, say, a torus, there's sort of two parts to constructing the Lefschetz vibration. We've got sort of like what Inosh was saying, you've got some Lefschetz crystal points that you can think about as happening sort of near the boundary, plus you've got a whole bundle area where you've got sort of actual fibers. So all of your singular fibers are sort of sitting over here. You've got a bunch of smooth fibers on the interior. You can construct this by first starting with a fiber bundle over the punctured torus, and then attaching your Lefschetz critical points to that. So this is how you construct infinitely many things. The idea is, because you've got that area, that bundle region over the interior of the torus, you can fiddle with things in ways that won't get seen at the boundary. So, so if we start with an F bundle over B, how is that going to contribute to the monodromy of the spinal open book? Well, if I sort of think about what's happening, say, on this loop right here. So if I sort of I just look at what's happening at this part of the fiber, the contribution to the monodromy coming from the base is sort of seen as what's happening as you go around to this particular loop right here, right? So if I want to figure out what the total monodromy is, I'm going to pick one copy of my fiber. I'm going to look at what the return map is as I isotope around this curve. And if I want to see what's happening out here, all I'm doing is adding the vanishing cycles according to this Lefschetz, according to Lefschetz singularities as I move out. So the monodromy is going to be, well, it's going to be whatever's coming from the base plus a bunch of Lefschetz singularities. If I think about what the bundle is, I've got some return maps that are determined by fundamental group of the base here, right? The bundle is determined by some sort of representation of the fundamental group into the mapping class group of the fiber. And if I think about what this curve is, like Inosh was saying on yesterday, this is then going to be the commutator of those diffeomorphisms. So the monodromy here is going to be some product of commutators. What am I going to call them? I'm calling them, I guess, AI, BI, times some number of Dane twists. So this part here, we have AI, BI, and DJ. Or these are just any diffeomorphisms of F, and the DJ have to be Dane twists. Okay. So the easiest thing to do then is to pick some some diffeomorphisms whose commutator is trivial. So that example that I was talking about at the beginning, where we're looking at a spinal open book whose page and fiber are both punctured tori, that particular contact structure admits infinitely many different Stein fillings, because you can fiddle with the bundle part in the interior in such a way that it won't be seen at the boundary. So for example, if I take F and B are both going to be punctured tori, and I've got this sort of two generators here now, I'll get sort of A and B. If I make A give me, say that, this is going to be confusing here. I'm going to be really kind of mean and use A and B in 3 different ways here. So A and B are going to be these two curves here. They're also going to represent the generators of the fundamental group, and they're also going to be the sort of Dane twists about those curves. Maybe I won't do that one because that's going to be confusing. So what I want is that this map over here, A is going to be just, let's say, a Dane twist about B, and B is going to be a Dane twist about B, but raised to the, let's say, the n power. Now the point is that because these are sort of... Okay, let's do that. All right, so I want those guys to be A, so let's call these guys alpha and beta. And then A is going to be the diffeomorphisms about beta. B is going to be the the Dane twist about beta raised to the n power. And A is the diffeomorphism we're associating to alpha. So as the two generators of the fundamental group of the torus, these are giving us the two different Dane twists, or two different diffeomorphisms that construct the bundle. So this description tells me, or will give me just some sort of bundle. If I look at what's happening at the boundary of the bundle, though, the monodromy is determined by this, by just what the commutator is here. But because these Dane twists commute, the commutator is trivial. So AB is 0 or 1, I guess, in a group.
When you use 2 of them, just use 1. If you want to create H1 torsion.
That's a good point. You
That's
only
how
need the
you
difference.
distinguish.
That's good. All you need is the difference between these two. So
So one element is in.
one element is enough.
Okay.
Yeah. Because what you're going to do is yeah. So the point is now we can actually now distinguish these different bundles because the homology of the bundle is different. And if I think about using whatever, let's say that the sort of the cell or the handle decomposition coming from that we would use to sort of build it, we're going to identify these curves with their images under the diffeomorphisms in the gluing map. So we'll pick up if we see what happens to alpha if we go around in the sort of A direction over the base. This curve is going to get glued to its image under the diffeomorphism. So it's a copy of A plus B. And if I look at what happens under the B direction, it's going to get glued to A plus n copies of B. Or we just forget about
Are
that.
these all surgeries on Lagrangian tori and the complement of the axes of T4? That's what it looks like you're doing. And if you do those surgeries on the base loop, the Lagrangian tori, base times fiber, you do them on the base, you're changing the monodromy.
Yeah, I think that's it. Yeah.
Yeah.
Yeah. So yeah, they're definitely easier ways of seeing this.
That's what
Yeah. So
That's surgery.
yeah. So yeah, you don't have to do it in 2 steps. You can, so let's forget about that.
You also want to make sure that that element doesn't die in the complement. Those Lefschetz critical points.
That's true. If you were going to continue this, that's right. If you were going to continue this, you would worry about additional Lefschetz critical points. But right here, we're just going to actually fill this with a bunch of different bundles. And yeah, they're all going to be what happens if you do block transform in the complement of a fiber. Yeah. Or fiber intersection. Yeah. Okay. So this is just sort of a random way of constructing these things. The feature that you need though is you need to guarantee that that your fiber and base are sort of complicated enough that you'll have room to sort of mess with things. So you need some genus or at least some essential curves in F in order to do this. So contrasting with say the annulus case where there's sort of nothing you can do, here we need some way of actually sort of moving these around. Okay. Do I have any time?
Yeah.
Yeah?
And so what are you going to do now?
Oh, so I'm going to say that. So this is it. So for each n, we get a filling x, and the point is that h1 of x is whatever it is, e cubed plus e mod n or something. So these are all different. Okay.
You could probably use relative Seiberg-Witten.
Well, this is a really good question, which is
Because you could get some with the same H1s.
Okay, so if we did sort of more complicated log transforms, this is exactly what I was wondering. So this is sort of a really like a clumsy way of getting some different fillings. So yeah, that's excellent. Yeah. Okay.
Or you could use some people's work like yours who already did it. I mean, you already have the constructions which would lead to this.
Yeah, no,
You can
absolutely.
fix the homomorphism type.
Yeah. Okay. So if you guys are okay with this, I'm going to be I'm just going to sort of give you a hint at how this works in higher dimensions, because that's kind of fun, and it's essentially the same thing. If you're okay with it. Yeah. No, I've got there's some.
No more
sad
hazing.
faces. Sad faces. How much time do I actually have here to punish you? Don't skip me.
Minus 1 minute.
The schedule said noon.
Yeah. No, it's new now. Okay, I'll be nice. So what I'll say is though, I'll be nice. If you're at all interested, this works exactly the same in higher dimensions. There's a bunch of technical issues about doing spinal open books in higher dimensions. They're the same technical difficulties that arise from doing normal open book decompositions. But the actual construction, if you once you can find some, there's ways of constructing contact manifolds in higher dimensions that have infinitely many Stein fillings that look exactly the same. I'll leave that as an advertisement in case you guys are interested in talking to me later. Other than that, I think I'm